Hi, everyone. Thanks a lot for coming. My name's Transon, and I'm the head of automation engineering at Notable.
I'm Jordan, and I'm an automation engineer at Notable.
And today, we're going to talk to you about finding flexibility at scale. This is something we think about a lot as automation engineers. To us, the concept of flexibility at scale is about finding a balance between two different worlds. On the one hand, you have high throughput lab automation, which traditionally works best when you want to do the same thing a lot of times. And on the other hand, you have the flexible, lower throughput world of assay development and R&D, which is harder to run at scale because every experiment is just a little bit different. So in this talk, we're going to cover how we develop automated systems in our lab with flexibility in mind, so that our scientists can change their workflows while still taking advantage of the automated tools available to them. But before we get into that, I want to give a little background about us. At Notable, our goal is straightforward. We're here to find better treatments for cancer patients. And to do that, we've developed a platform to improve clinical results and the drug discovery process. This platform is really the sum of everything we do at Notable, from hardware to software to biology. And this includes our high throughput drug testing platforms that generate a lot of data. It includes our machine learning driven approaches to help us gain insights from all that data. And of course, our ever-changing assays and workflows to give us more accurate results out of our platform, which is partially the driver behind this talk. These different aspects all come together to give us some predictive ability on how patients may respond to potential therapies, and ultimately determine which therapies will be most effective for groups of patients. In the end, it's about finding the right treatment for the right patient. Now, since we're both automation engineers, and this is a talk primarily about Green Button Go, for today, we're going to be focusing on the high throughput drug testing platform. This is a video of our labs. We're located in the Bay Area near Silicon Valley in Northern California. And what you're looking at here are some of the robotic work cells that we've developed at Notable to help us run these high throughput screens, where we test potential therapies directly on samples from cancer patients. All of our robotic work cells, including the ones you see here, are powered by Biosero's Green Button Go.
If you're unfamiliar with Green Button Go, it's a powerful tool that offers you the ability to build highly flexible automation platforms to help you operate at scale. I know that sounds a little bit like an oxymoron, so let's take a look at how we might be able to do this. There exists a natural tension between science and engineering, which comes from the nature of the work. Science is a very fluid and flexible process. When exploring a space, they tend to want the freedom to fully customize their workflows to explore the infinite and often unpredictable questions that arise from biological data. And when we're trying to do these things at speed, we like to reach for engineering solutions. But where science is this soft, squishy, stretchy place, engineering systems, well, they're a little bit more rigid. Oftentimes, they have to reduce the freedom of the science in order to optimize for throughput. This tension is exacerbated in R&D systems where the science is even more unpredictable. The scientists are still developing their workflows, and they don't necessarily know what they want the end product to look like. It's a bit like trying to build a plane while it's taking off. This makes it especially difficult to implement engineering solutions or automation. On top of the traditional rigidity of engineering systems, automation involves big, sometimes slow robots. There are lead times, teaching times, process development, and optimization. So it can feel like we're always playing catch up. As soon as you automate a thing, it feels like it's already changed. Historically, it's been very difficult to have it all. Science and automation, flexibility and throughput, the ability to both operate and adapt with speed. So why are we able to do this now? Well, in recent years, there have been significant advances to automation. We now have access to a variety of options for affordable collaborative robots. These robots are safe, they're flexible for the process, and robots are way easier to teach now. Personally, I have never touched a physical teach pendant. With Green Button Go, It's as simple as opening the teaching window, putting the robot in free mode, gently pushing it 90% of the way there, and then jogging it just the last little bit. And nowadays they have things like mobile robots and partial compliance, where you teach the robot generally where the nest is, but it'll wiggle itself the rest of the way down, which gives you way more flexibility in the process. Drivers for commonly used pieces of equipment are widely available. As users of Green Button Go, for the most part, we don't have to write our own drivers or worry about low-level commands. These things are taken care of for us, so we can focus on higher-level pieces of the process, like automating our workflows and procedures using the scheduling software. And this scheduling software comes with a lot of power right out of the box. We don't have to worry about coordinating all of our instruments or handling complicated timing for simultaneous processes. It can be as simple as dragging in a few steps, typing in our parameters, and kicking off the process. And it's only now that we can take advantage of all of these technological advances to create automation systems that are also very flexible, with the added benefit of being able to do so with a very small team. For example, Notable is a team of 50-something people, and we only have 2 automation engineers to handle all of our robotic work cells. As a small team, automating for a large scientific demand, we face a number of interesting challenges. Our scientists often want to run with a high-mix, low-volume mentality. Basically, that means that each experiment you're running looks a little bit different. At Notable, this manifests a bit like this. Each new primary sample we get through the door, we want to run a fully customizable experiment on it. This means a completely different set of compounds dispensed into a completely different set of wells. We may be trying out different antibody fluorophore conjugates to adjust for marker expression on the cell surface of a new sample type. Within our processes, we may only want to run a particular subset of the available steps or change the order that we're running them in. And when it comes time to read it out, since we never know quite how much sample we'll be getting, we want to be able to adjust the number and placement of wells that we're reading out. Now, most of our primary assays are pretty locked down. They're a set of canned steps for which we've optimized the parameters, and we're simply choosing which map files to use and which steps to run when. However, sometimes we may be asked to implement automation for a scientific process that itself isn't 100% developed yet. Here, we run into a scenario where we're trying to automate a process alongside its optimization. The question being, can we develop automation in parallel with developing science? Both of these scenarios are in and of themselves quite challenging, but in either of them, we may be subject to another type of challenge, which is deadlines. Science can be very opportunistic. The types of samples and projects available to us can change at any given moment. So in either of those scenarios, we may be asked to automate on extremely tight deadlines, automating a process in the span of weeks to take advantage of an exciting or time-sensitive opportunity.
And in practice, we don't deal with one challenge at a time. We often run into all 3 simultaneously. So let's set the stage for a time when we had to handle all 3 of these constraints: a high-mix, low-volume environment, parallel development, and tight deadlines. Let's talk about this situation where you don't have automation yet, but you want to start bringing it into your lab. Some of you may have seen or have been a part of a situation like this. Say, hypothetically, an R&D scientist comes to an engineer and says, "I've got this cool assay I want to run. Let's build a work cell to automate it." And everyone's on board. Yeah, let's do it. So they all sit down together, gather all the requirements of the work cell. Maybe the scientist sends over an SOP so that the engineer better understands the assay, and the engineer gets to work. Unfortunately, the timescale for hardware development can be a bit slow at times. And so 3 months later, our handy engineer emerges from their cave and says, "Okay, ready to launch, we've built it. This system does everything that you've asked for." And because R&D and assay development moves at a faster pace, the scientist basically says, "Oh, well, thanks, but I asked for these things 3 months ago. I don't really need them anymore. I'm doing something new nowadays." And one of the fundamental issues here is really a difference in development timescales. In the time that it might take for you to build a shiny, fully automated robotic system that does everything that you want it to do, well, the original reason that you built it for has probably already changed. And so when it was time for us to build a new screening work cell at Notable, this one was going to be our R&D work cell, we took the lessons learned from our previous build-outs and decided to develop this one in phases. The 5 steps that you see here are all pretty typical steps for developing almost any system. You start off by gathering requirements. What does this system need to do? You design your system. You build it. You implement it. Before you launch it, you verify. You make sure that the system works as intended. Does it actually do everything that it's supposed to do? Shortly after you deploy, you go into a maintenance phase. You keep a close eye on the system, make sure it's actually working as intended. If any errors pop up, you fix them, and so on. Now, there's nothing really wrong with these 5 steps, but as we saw in previous slides, if it takes months or sometimes a year or more to complete one round of this cycle, then you're going to run into problems in R&D. So what we wanted to do when we were building our R&D work cell was to still go through these 5 steps, but shorten this cycle from months to the span of weeks. And for us, this meant developing small chunks at a time, continuously deploying these chunks in lab, and constantly working closely with our scientists to figure out the next cycle. So when we built out this particular work cell, we started out with what you might call a manual work cell. This is pretty similar to what you'll see in a benchtop lab without any automation. You've got a few instruments and each instrument does a certain job. Here you've got an incubator, an acoustic dispenser, and a flow cytometer. And when a scientist is running an assay, they have to individually interact with each instrument. So in this example, they might have to walk over to the incubator, open it up, dig around for their plate, grab it, then they'll walk over to the acoustic dispenser's computer, tell the acoustic dispenser exactly which liquids they want to transfer from which wells at what volumes, manually load their plates, and so on and so forth. The first step where we get involved is what we call a sneakerware work cell. Physically, nothing's really changed. The scientist still has to move plates around themselves. Behind the curtain, though, there's a very important difference. We now have one software layer, one interface to deal with every instrument. In our case, this is a combination of our custom-built LIMS, Laboratory Information Management System, and Green Button Go. So here, we're introducing GBG into the process very early before we actually have any robotics. And so this time, when it's time to run the assay, the scientist just deals with one computer, one interface. GBG handles communication with all of the instruments, and the scientist just has to move plates around from instrument to instrument. Now, although there's no walkaway time in this phase because the scientist is needed at every step, a sneakerware work cell like this is still very helpful, as we've found that having GBG takes away this mental load of having to set up each instrument. You no longer have to think about, am I dispensing 40 or 50 nanoliters from this well? Which wells am I dispensing from? What voltages do I need to set on my flow cytometer? And so on. And as time goes by, we reach what we call a semi-automated work cell. So here, we've now got a robot arm to help us shuttle plates between instruments. And now our scientists can breathe for a little bit and walk away as the work cell automates portions of this process. But in this phase, it's still not fully automated. We've purposely built in these pause points, these areas in the assay where we've programmed GBG to hand the plate back to a scientist and wait for them to finish whatever they need to do. So in this phase, the process is partially handled by robots and still partially handled by people. And there's a few good reasons to have a semi-automated work cell like this. For example, you may not have all the instruments you need in-house yet. They could be expensive. You could be building up a justification to purchase them. You may have already purchased them, but you might be waiting for them to come in. Some instruments can have lead times of up to 3 months. And in that situation, it doesn't make sense to wait for 3 months for that instrument to come in. You should automate what you can with what you have now. In the theme of parallel development, you may not actually know if you need those instruments yet. You may not even know which instruments you need. But again, you still want to automate the steps that you're more sure of. So by adding these pause points in the middle of your process, that gives you the freedom to automate the steps that you're sure about while still leaving things open to your scientist's best judgment in other areas where you're more uncertain. And finally, as time goes by, we reach full automation. In this phase, you're more sure of the steps in your process and the instruments that you need. Here, a scientist is just needed to start a run, and the work cell automates the assay end to end so they can walk away for the end of the process. So we reached this phase, great, we built it, we're done, right? Of course not. So this is a true story. As soon as we built our R&D work cell to what we considered quote unquote fully automated, it turns out we had this great new opportunity to run this new assay that would give us a new dimension of data at a higher scale. And of course, this wasn't supported in the system that we just developed. But we didn't want to run this new assay completely manually. We still wanted to find a way to leverage automation to handle this assay. So when situations like this happen, the best thing we can do is take a step back and go back into a semi-automated phase. Again, you automate what you can. You automate the steps that you're sure of. We modified GBG to automate the steps that we could with the instruments that we had. And in other portions of the assay where we were still figuring it out, we programmed GBG to pause and hand the plates back to a scientist. And although this isn't a fully walk-away process, we found that this phase was still very helpful to our scientists as they were able to leverage our automated systems to run this new assay at scale and with a short turnaround time at the small cost of still requiring people to intervene at points in the process. And as we continue to develop the hardware and software, we can reach full automation once again. Over the years at Notable, we continue to jump between these two phases, from fully automated to semi-automated, back to fully automated, as we develop new assays at Notable. For us, work cells never really end because science never ends. The two have to be developed in tandem. Now, this approach of short development cycles, continuous deployment, and close collaboration is not a new approach in and of itself. Those of you in software development may be familiar with agile development. Those of you familiar with the word agile may cringe a little bit at the word. It can be a loaded word, and there's many different ways to interpret what exactly agile development means for your company. We call our approach agile automation, and to us, it's pretty simple. It's just an approach to work with the fact that requirements change. In fact, requirements change frequently. Sometimes requirements change so much, and we've found that in order to bring automation into this rapidly changing environment, we need to closely collaborate with the scientists developing the assays. We need to fully understand what they want to do. We need to implement these short development cycles and continuously deploy them in the lab. And by using this agile approach to developing work cells, by having these short deployment cycles, we found that it allowed us to reap the benefits of automation much earlier in the process. I spoke about these 5 phases, but keep in mind, our scientists were using our system from the beginning. So you get all the classic benefits. It reduces load on the scientists. There's more walkaway time. You get better traceability into what's going on, increased repeatability, and so on. It also ensures that by the time you reach the fully automated phase, at least until something else has to change, your work cell actually does what your company wants it to do.
But even when you reach your fully automated phase, we still want the power to fully customize the workflow so that no two workflows have to be exactly the same. This means dispensing different subsets of compounds, managing different plate layouts for dispenses and readouts, managing different sub-processes on each plate. How can we leverage Green Button Go to do this? One thing that we do is that we have a very tight integration with our LIMS. Having a tight LIMS integration allows us to leverage some of the more powerful tools in Green Button Go in intelligent ways, like swim lanes. Let's talk about the LIMS integration first. How does this integration actually help? This integration helps by keeping the work cell kind of dumb. Our LIMS is the source of data truth, so it's where all of the planning and information about an actual experiment lives. A scientist goes to the LIMS, plans a fully unique experiment, and then kicks it off on the work cell. Green Button Go facilitates the information flow between the LIMS in our work cell so that at the time of a run, Green Button Go will communicate with the LIMS and pull down all of the information it needs for a particular run. Which plates are involved, which transfers need to happen, which steps should be run in which order, and then finally, the work cell executes each run. But what about handling those variable process steps? Those steps that we want to either run conditionally or run in different orders. How does Green Button Go allow a plate to conditionally navigate the landscape of the process? One of the Green Button Go tools that we've used to handle modular and flexible processes is the use of swim lanes. What exactly is a swim lane? Swim lanes in Green Button Go are essentially a canned sequence within a process. They're a set of steps that are always run in a particular order. And you can think of the swim lanes kind of like Lego blocks, where you can take these modular chunks and stitch them together however you want to create a custom experiment within a given process. What might that look like? Well, here we have a basic example. You want to do a dispense, and then you want to do a basic plate readout. Along the way, you may want to do a second optional dispense and maybe even a third optional dispense using a different piece of equipment. Each of these swim lanes is being executed from a work list. So as each plate finishes its current swim lane, a procedure is run to determine which work list, if any, it should be shuttled to, and then which swim lane should be executed on this plate next. This allows us to have a very large and complex workflow that can be broken down and run in as many possible combinations as we can think of.
So this has been a somewhat short talk, but hopefully we've shown you a few ways that you can intelligently design and build automated systems in your lab to handle flexibility with the help of Green Button Go. This includes agile automation. It means continuously launching your work cells in small chunks in phases with Green Button Go so that you can use automation from the beginning. It includes designing these high-level experiments in your LIMS and then using GBG to communicate with your LIMS to parameterize and run all these different experiments. It also includes using GBG swim lanes so that you can mix and match these canned sequences to create a complete work cell, a workflow on the fly. And if there's an underlying theme to this talk, it's that technology moves fast and we have to move with it. As automation engineers, we love robots. They're pretty cool. But in the end, what matters isn't the type of robots that we use or the exact technology stack that we've developed. It's about what we're able to do with this technology. It's about what we can achieve by constantly adapting and moving. At Notable, these approaches have allowed us to quickly make an impact on cancer treatment discovery with a small team. And as technology continues to move forward, I can't wait to see how you all bring flexibility and automation together in your industry as well, whether you're speeding up the drug discovery process, streamlining biomanufacturing through synthetic biology, or finding better treatments for cancer patients. Technology moves fast, and we have to move with it. Thank you.